All right, we're gonna start here. There is extra credit Friday. So what is that date? 26, I think, Friday. So on Friday, 6 o'clock, we're gonna have pizza in here, and at 7 o'clock to 8 o'clock is the extra credit. So you can come for pizza. 7 to 8 p.m. in this room is extra credit. I'm going to send out an email. So if you don't get the email, though, send me an email saying I need information on the extra credit Friday. It's also going to be on a Google Meet. So if you can't come here, you can still participate. All right, dilutions. So we're going to change our concentrations. M1 V1 is equal to M2 V2, or initial and final. All right, the units here, they have to be the same. Doesn't matter what the units are. Capital M is molarity, and that is moles of solute per liter of solution. All right, so when you're making a solution, you have your solute, you have your solvent. All right, so solute can be a liquid or a solid. Let's say we have NaCl, that's a solid. Solvent, universal solvent, pretty much the only solvent we're going to talk about is water, but we might have some alcohol solutions as well. But 90+% of our solvents are going to be water. And then when you mix that, you have salt water, which is a solution. All right, and so when we are getting the molarity of this solution, we take the moles of the solute, the moles of the solute. We do not divide by the liter of water. We divide by the liter of solution, and the solution is the NaCl plus H2O. All right, so it is moles of solute per liter of solution. If you have a very dilute solution, the very small amount of solid doesn't change the volume of the water. However, if you have a very concentrated solution, that changes the volume dramatically. So it is always moles of solute per liter of solution. All right, and when you are diluting something, you will normally, when you're making a molar solution, you're going to use a volumetric flask for that, where it has the one line. We've used them in lab. And it is then the volume of both the solute that you dissolved and the solvent. So it's the solution volume to that mark. All right, so if we have 1.52 grams, we have to convert that to moles. So you get the molar mass of the potassium dichromate, 2 potassiums, 2 chromiums, 7 oxygens, add them up. And that's going to give us our moles of solute. We're going to put it in a 50 ml volumetric flask, add enough water to bring it to the mark. All right, so then the total solution, so they are both in there together up to the 50 ml mark. All right, and so now again, you do not have to show this conversion if you just know M is 10 to the minus 3, so that is 50.0 times 10 to the minus 3 liters. And if you plug that into your calculator, it knows how to work that. If that's your final answer, that is not acceptable scientific notation. You would have to put it into proper scientific notation. All right, so, but to get the conversion, that's the conversion that your calculator needs for you to do the problem. All right, so 294, that is your molar mass. All right, so this would be given. 294 is your molar mass. If you are going to calculate the molar mass, if it's not given, you have to give 2 decimal places. If they give it to you, you use what they give you. All right, so they gave the mass at 3 sig figs, so they gave the molar mass at 3 sig figs, and they gave the volume at 3 sig figs, so be sure to give your answer to 3 sig figs. And so you get your answer here. That's your moles after the grams cancel. And there is your volume in liters. You simply divide those two numbers, and that is your moles per liter. And when you divide those two numbers, you get 0.103. And then you just have a capital M for molarity. All right, if we have a 0.154 molar NaCl, you have to know what that means. We have a 0.154. This capital M is not helpful. You have to say that you now have moles of, not solute, doesn't help either. NaCl, that's what we have moles of. NaCl, you have to recognize your solute per liter of solution. All right, so capital M doesn't help. That doesn't help you do anything with units. You have to put in what that means, moles per liter. All right, so how many moles of NaCl are contained in 500 milliliters? So now you see that we simply will multiply this by liters. So 500, we know M is times 10 to the minus 3, and liter. All right, so that is 500 times 10 to the minus 3 liters. Or you can go right to 0.500 liters. It doesn't matter how you want to do it. You don't have to show your work to go from milliliters to liters. You can, you don't have to. I am not grading the show of the work of that. All right, and so when you do that, you get a 0.077, and you have to put the 0. All right, so the most common error here is sig figs. All right, moles is the second. All right, so you have to have the number to the correct number of sig figs. You also have to have the units. All right, so you have, the calculator is going to say 0.077. You have to know you have 3 sig figs, and you also have to know that the leading zeros are insignificant. So you must give that to the correct number of sig figs. Then it says how many grams of NaCl are in this solution. So now we need grams per mole, which is on the periodic table. So you add up sodium 22.99, chlorine 35.45, and you get a 58.44. So you have 58.44 grams per 1, if you don't like it to be there by itself, mole. Grams per mole means grams per 1 mole. And so when you multiply that, you get 4.50 grams. And then again, here they're giving it, instead of the 0.4, they're giving it as 58.4 because they're giving it to 3 sig figs. All right, so again, if you're off by the last digit, that is fine, because remember, significant figures, certain number, and then a number having some uncertainty. All right, saturated. Saturated means you're putting in a bunch of solute. So saturated means that you have NaCl, except now you basically fill the beaker with NaCl, and then you add a small amount of water. So then you add a little bit of water, and what you end up with is this water that's stirred, but there's still NaCl at the bottom. So saturated means you added too much solid. It will not all dissolve. All right, and so if you do that with NaCl, that solution is a 6 molar solution. 6.00 moles NaCl per liter of solution. Again, capital M is not helpful at all. You have to know what that means. All right, so how much of this solution is needed to prepare 1 liter of 0.154, which is physiological saline solution? So now we're doing a dilution. We have something that is more concentrated, 6 molar, and we want to make something that is less concentrated, 0.154 molar. So for all dilutions, MV is equal to MV, diluted, undiluted. All right, so it doesn't matter where you put it, but if you're putting the 6 molar on the left side, then we need the volume of the 6 molar. And then if we are putting the 0.154 molar on the right side, we need the volume of that. And the volume of that is given. All right, and so we're going to need 1 liter. All right, so when you do this, you simply divide both sides by 6 molar. So the molarities cancel here, the molarities cancel here, and now you've got your volume in liters. So the molarity is always moles per liter. The volume can be any units, but they have to be the same. So when you take your 0.154 and divide it by 6, you get 0.0257. And that's in liters. All right, so you might want to put that into milliliters. You don't have to if it doesn't say what is the volume in milliliters. But if you're in lab and you want 0.0257 liters, no, you want 25.7 milliliters. So you get out your 100 mil graduated cylinder or your 50, and you measure out 25.7 mils of the 6 molar NaCl. So we need 25. So right here, the volume of that 6 molar, we need 25.7 mils. We're going to stick that in a 1 liter volumetric flask, and then we're going to add water until it hits the 1 liter mark. That's how you would do the dilution. So 25.7 mils of 6 molar NaCl will go into a 1 liter volumetric flask. Then you will add enough water to reach the mark. All right, so now we're going to do quantitative analysis. Quant is how much. All right, so we're going to do quant. That means you need a number. Quantitative analysis, when we did our sand salt, how much sand, how much salt. All right, it wasn't a qualitative analysis where I gave you an unknown and I needed you to tell me if that was sodium chloride, potassium nitrate, sodium nitrate. That would be qualitative. What is it versus quantitative? How much is in there? Gravimetric analysis. In order to do this, we're going to run a reaction that gives a precipitate, and then we're going to measure the mass of that precipitate. All right, so here is a precipitation reaction. So you have barium nitrate with potassium chromate. All right, all nitrates are soluble. All potassium salts are soluble. So both of these are soluble. So if we're doing the molecular, we have BaNO3 sub 2 plus K2Cr2O7. All right, and both of those are soluble. Now we're going to do a double replacement reaction. All right, and so the barium goes with the chromate, so we get barium chromate, Cr2O7, and that is not anything on your list to memorize. All right, so I would have to tell you that the barium chromate is insoluble. And so when you know that, that means you have a solid. And then you would have potassium nitrate. All right, and so to balance it, we would need 2 potassium nitrates, and we have a balanced chemical reaction. All right, so all nitrates are soluble, so this is a strong electrolyte. All potassiums are soluble. This is a strong electrolyte. I would tell you that this is insoluble, which makes it a weak electrolyte. And this is a potassium all soluble, nitrates all soluble. This is definitely a strong electrolyte. So strong electrolytes will break up. So here you will get barium plus 2 and 2 NO3 minuses. You will break up all strong electrolytes, 2K plus and Cr2O7 minus 2. All weak electrolytes are going to stay together. All right, and so you have BaCr2O7, that is a solid. And then you have 2 K pluses and 2 NO3 minuses. And so you will then, that's your ionic. So this is your molecular. This is ionic. So the net ionic, we canceled the exact same ions on both sides. The barium plus 2 is not going to cancel. The nitrate is going to cancel. The potassium is going to cancel. This did not cancel. And so your net reaction is the barium plus 2 reacts with the dichromate, Cr2O7 minus 2, to give the solid BaCrO4. Cr2, oh, good Lord. Okay, that's got to be confusing as heck. We are not using dichromate. We're using the regular chromate. Yeah, it works also with the dichromate, but yeah, that's not the question. All right, so that should be a regular chromate, not a dichromate. Again, that doesn't matter, but that could be confusing. All right, so you have your chromate, not the dichromate in this case. So that is going to work the same. If you did the dichromate, you would still get the yellow precipitate. All right, so this is then called formation of a precipitate. So PPT is the abbreviation for precipitate. All right, and so the things that canceled out, what you don't see in the net ionic, those are called spectator ions. So your K plus and your NO3 minus are spectator ions. So anything that was in the molecular and the ionic, but not in the net ionic, those are your spectator ions. All right, so whenever you have a solid, then you filter it, and then you dry it, and then you weigh it so you can get a mass. That is called a gravitational analysis, gravimetrical analysis. All right, because the filtering is going down by gravity. All right, so a soluble silver compound was analyzed for % silver by adding sodium chloride solution to precipitate the silver ion as silver chloride. All right, so we have 1.583 grams of silver. All right, so this is a soluble silver compound. All right, so this is a soluble silver compound. That means that we have Ag plus, okay? All right, and so when we added the silver chloride, all right, so we have Ag plus, and then we added sodium chloride, NaCl, all right, so we added some sodium chloride solution. All right, so all sodiums are soluble. All sodium's always a spectator ion. All right, and so what you get is you get AgCl solid. So the net ionic, since sodium is always a spectator ion, your net ionic is simply Ag plus with Cl minus gives AgCl solid. All right, so now we have a solid. So then we can filter that solid, dry the solid, weigh the solid. All right, and so it gave 1.788 grams of silver chloride. So we know that this is 1.788 grams of silver chloride. All right, so we know the % silver in silver chloride. We just use the molar masses. So silver, you look on the periodic table, it's about 107. You have a periodic table, accurate value, 107.87, 107.87. And chlorine is 35.45. So you add that up. $143.32. All right, so we can get our % silver in silver chloride. It is simply the silver. So if we want % silver in AgCl, it is the molar mass of the silver, which is 107.87, divided by the molar mass total of the AgCl, 143.32. So when we push the buttons, we know that the percent silver in silver chloride is 107.87 divided by 143.32 times 100, 75.27%. Oh, we need another one. That is 5 sig figs and 5 sig figs, so 75.265%. All right, so now we have a mass of silver. That is 1.788 grams of silver chloride. So we know that 75.265% of that is silver. The other 24.735% is going to be chlorine. All right, so we want to take 75.26% of 1.788 grams. So put that in a fraction form, 0.75265. All right, so we multiply that, 1.78 times that answer. 1 point, and this is going to be 4 sig figs. So we know 1.346 grams of silver. All right, so we took our silver compound and then we added chlorine and made silver chloride. We can analyze the silver chloride. We know exactly how much silver is in there. It is 1.346 grams of silver. All of that silver came from this compound. All right, so it came from a soluble compound. Compound is not just Ag+, it is AgI, Ag soluble, so it's probably silver nitrate. Not many other choices. So chances are this is going to be silver nitrate or some other soluble silver compound. Yeah, normally it's silver nitrate. All right, but anyway, we can get the percent silver. So we know that 1.346 grams is silver of this 1.583 gram silver compound. Right, and so when you divide that by 1.346 divided by 1.583, you get 85.01%. I'm interested to know what is that compound. All right. All right, so again, you have your silver chloride, and we're going to get the percent silver by taking the molar mass of silver and dividing by the molar mass of the silver chloride. And that's how you get the amount of silver in that compound, in the silver chloride. We know that all that silver came from the soluble compound. All right, and so you take that number that we precipitated out, that amount of silver, divided by the silver compound times 100. And you get 85.03. So remember, sig figs, you have certain number, certain number, certain number, and then the last number will have some uncertainty. So again, if you get 85.01 or 85.03, that is the same answer. It's just a rounding, how people round, how people give the molar masses. So that is the same answer. All right, so that is for forming a solid and determining your percentages. A titration is using liquids. So a titration, you're going to have a liquid, a solution measured out. You're going to know that concentration. You're going to then add that known solution to an unknown solution, and you'll have an indicator. And when it changes the correct color, then you will write down that volume and do all the calculations. All right, so here is a titration. And so it looks like you got phenolphthalein. So it's probably a typical acid-base reaction where you'll have your NaOH here. You're going to have your HCl or some other acid here. And you're going to have phenolphthalein. And when you add enough base, then you'll get a light pink. If you add too much base, you'll get a dark pink. All right, and so For phenolphthalein, you want a nice light pink endpoint, and then you know that it is neutralized, and you will end your titration and get your volume. All right, and so that is called a volumetric analysis because we are adding a volume. The volume of HCl will be here. The volume of NaOH will be here. All right, so it's a volumetric analysis. And it is based on a titration experiment. All right, so now we have a question here. Zinc sulfide reacts with hydrochloric acid to produce hydrogen sulfide gas. How many milliliters of this 0.0512 molar HCl are required to react with 0.392 grams of zinc sulfide? All right, so this is a balanced chemical reaction. Remember, we have to always work in moles. All right, so we're going to take our 0.392 grams of zinc sulfide, and we're going to convert that to moles. And so we go to our periodic table, and we find our zinc, that is 65.41. And then you find your sulfur, which is 32.07. And you have your molar mass. 97.48. So you have your 97.48 grams of zinc sulfide per mole of zinc sulfide. So grams of zinc sulfide canceled. The reason why we want to do moles, again, remember how you read the reaction. 1 mole of zinc sulfide reacts with 2 moles of hydrochloric acid to produce 1 mole of zinc chloride and 1 mole of hydrogen sulfide gas. All right, so you read those as moles. So now we want HCl. We see that 1 mole of zinc sulfide, so that it will cancel the moles of zinc sulfide, will produce 2 moles of HCl from the balanced chemical reaction, moles of zinc chloride. All right, so here's where the problem comes, because no one knows, but I keep telling you, you must know, capital M is not useful. You have to know what that means. That means you have 0.0512 moles of HCl per liter of solution. All right, so if you know that, we know that we want moles of HCl to cancel, so we have 0.0512 moles of HCl per liter of solution. All right, and so that's how many milliliters of this solution, this 0.0512 solution, that we will need, not in milliliters, but in liters. So again, you have to get rid of your liters and go to milliliters, and we know M is times 10 to the minus 3. So when you push your buttons on your calculator, you got your 0.392 divided by 97.48 times 2 divided by 0.0512 and then divided by 1 times 10 to the minus 3. And it will require 157 milliliters. So you would have to add 157 milliliters of 0.0512 molar HCl to react completely with the 0.392 grams of zinc sulfide. All right, so they do the same thing. Their molar mass, again, is slightly different. That's fine. All right, then they push the buttons, and then they convert it to milliliters, and they get the 157. All right, so grams, you always go to moles. You get a balanced chemical reaction, it has to be moles. You have to use the mole ratio in the balanced chemical reaction. You have to know what molarity means. If you just have capital M and you don't know what that means, this one is impossible. Make sure you know that molarity is moles of solute, in this case, the HCl, per liter of solution. All right, a dilute solution of hydrogen peroxide, H2O2. Is sold in drugstores as a mild antiseptic. A typical solution was analyzed for percent hydrogen peroxide by titrating with potassium permanganate. All right, so in the store, normally you will buy 3% H2O2. All right, that is what is sold at the store. If you're getting a perm, you'll get 30%. For a pool, you'll get 27%. All right, so there's a lot of different percentages of hydrogen peroxide out there. All right, so to analyze it, we're going to titrate it with potassium permanganate, KMnO4, nice purple solution. All right, and here is the balanced chemical reaction. Not sure why they did it quite that way, but okay. All right, so here is the balanced chemical reaction. What is the mass percent of hydrogen peroxide in the solution if we take 57.5 grams of solution, and that requires 38.9 mils of 0.534 molar KMnO4 for the titration. All right, so what we want to know is how much hydrogen peroxide there is. All right, here is the hydrogen peroxide. So when you're talking about a hydrogen peroxide solution, the other 97% is simply water. All right, so your 3% hydrogen peroxide is 97% water. All right, you got 30%, the other 70% is water. All right, so there's going to be some percent of this solution that is water, and the other percent is hydrogen peroxide. All right, so the question is, what is the mass percent of hydrogen peroxide? So to get the mass, so in order to get the mass percent, we need the mass of hydrogen peroxide divided by the mass of the solution. We already know that. That is 57.5 grams of solution. All right, so in order to answer this question, you have to figure out, what am I even looking for? All right, what you're looking for is the mass of hydrogen peroxide. We get this information from this balanced chemical reaction, which has hydrogen peroxide right here, and it has potassium permanganate right here, and we're going to do a titration. And this solution required, and of course the water is not reacting at all, only the H2O2 is reacting with this, and so it required 38.9 mils of 0.534 molar KMnO4. Again, you have to know what the molar is. So we have 0.534 moles of KMnO4 per liter of KMnO4 solution, and we have 38.9 milliliters. So again, I don't care how you do it. You can go right. I would prefer it to say 38.9 times 10 to the minus 3 liters, but however you convert this to liters, this is liters, and you have to have liters to cancel it. So convert this to liters. If you want to go to 0.0389 liters, great. If you want to show your work and write it in, great. However, you have to go to liters. So now we have moles of KMnO4, and now we have a balanced chemical reaction. We have a balanced chemical reaction for a reason. It is a mole ratio. 5 moles of this react with 2 moles of that. That is what we need. We have 2 moles of KMnO4, we put it there, so the moles of KMnO4 cancel the moles of KMnO4, and we have 5 moles of H2O2 from our balanced chemical reaction. All right, we need the mass of H2O2, and so simply get the molar mass. So we have 2.02, we have 32, this is 2 H's, this is 2 O's, and so the molar mass is 34.02. So now when we put in our 34.02 grams per mole of H2O2, moles of H2O2, and we have the mass of H2O2, which is what we need to put in our numerator. All right, so when we push the buttons, we have our 0.534 times our, put it in the calculator, 38.9 negative 3, or the negative button 3, not minus 3, the negative button 3, times 5, divided by 2, times 34.02. and you get 1.77 grams. 1.77 grams. So now we're going to take our 1.77 grams, because that's what this equals, 1.77 grams H2O2, and we divide that by our total, which is 57.5 gram solution, times 100. So I'm not going to clear out my calculator, so mine is 1.7667, divided by 57.5, and I get and then times 100, then I get 3.07%. So this is right off of the usual 3%. All right, so this is 3.07% H2O2. That is what you normally get on the shelf at any store, 3.07%. All right, so it depends. If you have one that is brand new, you probably got 3.07%. If you got one that's, a year old and it's almost expired, it's probably 2.5%. It just keeps going down over time. And if it's expired, well, some of it is 0% hydrogen peroxide. It is just all water. All right, so they'll show it to you. Again, they do it the same way. They just simply change the M to what M is, 10 to the minus 3 liters. Leave it as 38.9. Plug it into your calculator. It knows how to do it. 38.9 E minus 3 times 0.534 times 5 divided by 2 times 34.01 is what they have instead of 2. Doesn't matter. We're only given 3 sig figs. We will get the 1.77 grams. We will then get the 3.07% H2O2. All right. All right, so let's look at this oxidation reduction reaction. All right, so how you're going to do this oxidation reduction reaction is you have to assign your oxidation numbers. All right, so any element in its natural state has an oxidation number of 0. Your halogens, always in binary compounds, 2 elements in a compound, they're always -1. All right, so each of the iodines here, -1. That makes this iron a +3. Because +3 and 3 -1s gives you a neutral compound. Over here again, the I is -1. Halogens in binary compounds are always -1. Mg is always +2. All right, so iron could have been 2 or 3. Magnesium can only be +2 in compounds. So column 1, all right, your alkali metals, always +1. Alkaline earth metals, column 2, which is your magnesium, that's always +2 in compounds. All right, so we see that our iron is going from a +3 down to a 0. +3 down to, reduced to 0, reduction. All right, we see that our magnesium's oxidation number is going from a 0 up to 2. It is increasing oxidation. This is oxidation state. That is our oxidation. All right, so the iron +3 is reduced down to iron 0. Your magnesium 0 is oxidized up to magnesium +2. All right, and so you have to have, in any balanced oxidation reduction reaction, you have to have your electrons be the same gained as lost. So our reduction for iron +3 to go down to 0, we have to gain 3 electrons per Fe because electrons are negative. So if you have +3, you have -3, you have 0. For your oxidation, we have to lose 2 electrons per magnesium. For our 0 to go to a +2, we have to lose 2 negative charges. All right, so any oxidation reduction, you have to have the same number of electrons lost as gained. This is obviously not balanced. 3 is not the same as 2. The least common multiple is a 6, so we have to do the iron 2 times. So we do this times 2. The iron has to be done 2 times. Magnesium has to be done 3 times, times 3. All right, 3 times. And so now we have 6 electrons gained and 6 electrons lost. All right, and so then you also see that when you put the coefficients, I put the coefficient there instead of here. All right, so when you put the coefficients in, you have a balanced chemical reaction. Now you see you have 2 irons, yes, 2 irons, 3 magnesiums, yes, 3 magnesiums. Now the iodines are also balanced. We have 6 of them on the left and 6 of them on the right. All right, but the key is you have to see how many electrons were gained and how many electrons were lost in this oxidation reduction reaction. You have to know what was oxidized, what was reduced. You also have to know that if we wanted to oxidize our magnesium to magnesium +2, we are looking for an oxidizing agent. So the iron iodide, iron 3 iodide, is our oxidizing agent. If we wanted the iron to be reduced down to iron 0, we would need a reducing agent, and that would be the magnesium. All right, so you have to be able to label the oxidation half reaction. That would be the magnesium going to magnesium +2. The reduction half reaction, which is the iron going to the iron 0, iron 3 going to iron 0. And then you would have to label the oxidizing agent, which is the iron iodide, and the reducing agent, which is the magnesium solid metal. All right, so you have your oxidation half reaction. That's the magnesium going to magnesium +2. You got your reduction. That's the iron going iron +3 going to iron +2. And when we do our oxidation reductions, we look at our net ionic. All right, so all halides are soluble except for silver, mercury, and lead. So this is going to go to Fe +3 and I minus, so 3 of them. And over here, again, all halides are soluble except for silver, mercury, lead. So your Mg +2 is soluble. You got your I minus, you're going to have 2 of those. All right, the reason why we're not looking at the iodine, because we're doing oxidation reduction. This is -1, this is -1. This doesn't change oxidation. So if you're not changing the oxidation, you're not part of our oxidation reduction balancing electrons. And so that's where the iodine went in this reaction. It is going to be a spectator ion because it is soluble in both the reactant and the product. All right, so this again is where when you have your 2 and you have your 3, you have to have the same number of electrons gained as lost, and so that's why you would have to multiply this one through by a 3 and multiply this one through by a 2, and then you see the 6 electrons lost is equal to the 6 electrons gained. Remember, lost is given off, is a product, gained is a reactant. And when you add them up, you have this net ionic. All right, so that is your net ionic. Your molecular would have been the first one that we have here. So if it just says balance the reaction, it doesn't have to be, either one would be fine. But regardless of the way you do it, the question of oxidizing agent, reducing agent, oxidation half reaction, reduction half reaction, how many electrons were transferred? 6 electrons were transferred, 6 electrons gained, 6 electrons lost, 6 electrons were transferred. All right, so they give the net ionic, and then they also give the molecular. I would not require both of them. You can give either one. Most people, for the oxidation reduction, go to the molecular, but I would accept either one. Again, molarity capital M. Make sure you write down the units for capital M always. All right, oxidation numbers. These should be very simple. If you can't get the oxidation numbers correct, you cannot get the oxidation reduction correct. If you can't get the oxidation reduction correct, don't just skip it. Get the oxidation numbers right and get some partial credit. Oxidation numbers should be very simple. This is the hardest one I can give. If you can do this one, you can do all of them. This is the very hardest oxidation number question. You have to know that oxygen in compounds is -2. So this is a total of -14 because each O is -2. There are 7 of them. That gives you -14. You see that -2 or 2 minus is your overall charge. So your chromium's not +14. It would be +14 if that was neutral. It is not neutral. It is -2. So this is a +12 because 12 minus 14 is equal to -2, which is our overall charge, which is what it has to be. All right, but it didn't ask for what is the oxidation number of all the oxygens, so it wouldn't say, you wouldn't give -4. It's -2 for the oxygen's oxidation number. It doesn't say what is the oxidation number for all of the chromiums. It says what is the oxidation of Cr. So Cr is +6. The reason why it's +12 is because there are 2 6s, which makes it +12. All right, so if you want the oxidation numbers, they are chromiums +6, oxygens -2. But since we have 2 chromiums, that's +12. Since we have 7 oxygens, that's -14. And it adds up to -2 because that is the charge given in the question. All right, so if we're doing KMnO4, and so if we do KMnO4 and then K2MnO4. All right, so the rules. Oxygen in compounds is -2 unless it is hydrogen peroxide or a peroxide where it's -1. All right, so in compounds, -2. So that's -8 because each oxygen is -2. Potassium, column 1, always +1. In compounds, anything in column 1 is going to be +1. All metals in column 1 are going to be +1. So potassium is +1. All right, so this time we're neutral. There is no charge given here. So we need a 1 plus a number plus -8 to equal 0. And that, of course, is a +7. So Mn here is a +7. Because 1 plus 7 minus 8 is equal to 0. You would do exactly the same thing here, except this is +2, this is -8, because each oxygen is -2. Each potassium is +1. You have to find the missing number, and you have to look at the charge. If there's no charge, that means it is neutral. So here you see 2 plus what number? -8 is equal to 0, and that, of course, is a 6. So +2 plus 6, that's +8, -8, 0. All right, we're not looking, the oxidation of oxygen is not -8, it's -2. It's -8 because we have 4 of them. All right, so again, going through the rules, elements, 0. Monatomic ions are whatever the charge is. So if you have Fe +3, it's +3. If you have Fe +2, it's +2. Oxygen is -2 in compounds, unless you have a peroxide. All right, so that's when you would have a -1 for the oxygen. Hydrogens are in first column. Note I see metals. All the metals in the first column are always +1. Hydrogen's not always +1. Most of the time it is +1. The only time it is -1 is when there's a metal first. If you have a metal and a hydrogen, then your hydrogen is -1. All All right, so again, it has to be with a metal first and then hydrogen, and that's when your hydrogen is -1. Your halogens in compounds, in binary compounds, are going to be -1. Note that if we have a perchlorate, ClO4 minus, all right, that's not a binary compound, right? That is a polyatomic ion, so chlorine is definitely not -1 here. All right, oxygen is always going to be -2 unless it's a peroxide. All right, so you have -8 here. All right, you need a number that is going to give you a -1. So you see that chlorine here is a +7. So the oxidation number of chlorine is +7, because +7 minus 8 is equal to -1, which is the given charge. All right, now if you're talking about calcium chloride, CaCl2, now we're talking calcium, that is always +2, and then chlorine is -1. All right. So in binary compounds, it's going to be -1. So binary compounds, -1. This polyatomic ions are not binary. All right, so they will be whatever you get when you calculate the oxidation number. All right, and then again, if you have an overall charge of -1, you add up your oxidation numbers, they have to equal that overall charge. If your overall charge is neutral, well, then your +2 and your 2 -1s have to be neutral. All right, so they always add up to the overall charge. All right, so on the test, you're going to be given this. All right, so this would be the very hardest question that I could put on the test. This is the molecular equation, and on the test, it will say give the molecular, ionic, and net ionic. All right, so you're going to do a double replacement. So here you have to know that your CO3 is -2, that's carbonate. All right, so you have your copper that's going to go with your chlorine. And so you're going to have CuCl2. You have your carbonate, which is going to go with your hydrogen. And so you're going to have H2CO3. But then, this one is the hardest one I can put on the test, because you have to remember that carbonates and acid, that is your volcano reaction, H2CO3 quickly decomposes into H2O and water, and CO2. H2O is water. All right, CO2 and water. So it is not the carbonic acid. It is CO2 and water. That's why this is the hardest question. All right, so then it's the typical every question when you do molecular ionic and net ionic. Is it soluble or insoluble? So you have to know your rules. All right, and the rule is if you are a carbonate, you are insoluble unless you're going to be a lithium, potassium, sodium, or ammonium. And this is copper, so this is insoluble. All right, so that makes it a weak electrophile. HCl, that's an acid. You have to have your 6 memorized strong acids. So that is HCl, HBr, HI, HNO3, HClO4, and H2SO4. And so obviously HCl is one of the 6 strong acids. If it's a strong acid, then it is a strong electrolyte. All right, copper chloride. You have to know that all halides are soluble unless you're silver, mercury, or lead. This is copper. This is soluble. All right, so this is a strong electrophile. Soluble. Anytime you have a soluble ionic compound, that is a strong electrophile. It's going to break up completely. All right, so CO2 is a gas. It is a molecular compound, which makes it a non-electrophile. Same with water. That is a non-electrophile. So both your CO2 and your water are not ionic, and so they are molecular. They are non-electrophiles. All right, so weak electrophiles, if they're a salt, they stay together and they're a solid. So CuCO3 is a solid. All strong electrophiles break up. And so this is 2H plus and 2Cl minus. All right, all soluble ionic salts will break up, Cu plus 2 and 2Cl minus. Any solids, liquids, or gases remain together. CO2, gas. H2O, liquid. All right, so you're only going to break up the aqueous ones. The only aqueous ones that don't break up are your weak acids. All right, so then when you see your ions, you have 2Cl minuses on both sides, and that's it. So your net ionic is CuCO3 solid plus 2H plus yields Cu plus 2 CO2 and water. All right, so that is by far the hardest one that I could put on the test. And your spectator ions, there's just one. That is the Cl minus that canceled on both sides, but 2Cl minus, it doesn't matter. But Cl minus was in the initial reaction, but not in the net ionic. It is a spectator ion. So acids, carbonates, CO2, and water. That is why that one is the hardest one to do. So this is called formation of a gas. All right, so you got formation of precipitate, formation of a gas, and you have neutralization. Those are the three types of double replacement reactions that we have. All right, so here are the ones that you need to know for the gas formation. These are by far the hardest ones. All right, so it's simply a double replacement here, except the H2S is a gas. And so that is formation of a gas, a hydrogen sulfide gas. So a sulfide with an acid is going to give hydrogen sulfide gas. We already did the carbonates, CO2 and water. The sulfites, so are going to work the same as the carbonates. So this is CO3 minus 2. This is SO3 minus 2. Anytime you react those with an acid instead of CO2 and water, you get SO2 and water. All right, so the formation of the gas ones, acids with carbonates, acids with sulfide, acid with sulfites. Those are the ones that are hard to remember. If you just do a double replacement reaction, you will get a lot of credit. You will not get full credit, but you would get a lot of credit. You would get most credit for this one because, well, I guess the credit that you're going to miss out on is what kind of reaction is it. If you don't get gas, you're not going to get formation of a gas. All right, so it's going to be, is it a precipitate, is it neutralization, or is it formation of a gas? So if you don't recognize that that's going to give a gas, then you won't get those points. All right, so this one would be an easier molecular ionic and net ionic. All right, none of them are easy. This one is easier because it is a true double replacement with not remembering the CO2 and water, the SO2 and water. Here you've got your H's that are going to go with your OH's, and that's going to make HOH, which should be written as water. Here you're going to have your potassium that's going to go with your sulfite. All right, and so this one could be a little strange because you're like, wait a minute, sulfites are going to give SO2 and water only if they're with acids. Okay, so that is not the case here. This is simply an acid plus a base is going to give water and salt. Now, the definition of salt is simply ionic compound. All right, so if somebody wants salt, well, table salt is NaCl. But technically, if somebody says, you know, I want salt, you can give them any ionic compound, that's a salt. All right, some of them are poisonous. So, of course, you want to give them sodium chloride if they ask for salt. But in general, a salt is any ionic compound. But it is understood if you want salt, you want NaCl. If you want sugar, you want sucrose. You don't want any carbohydrate, you want sucrose. All right, so this is acid base gives salt and water. So this is a neutralization. So now we've seen them all. You're going to get gas formation, solid formation, which is formation of precipitate, and now you have neutralization. All right, so here you have to know that this is not one of the 6 acids that I wrote down. So this is a weak acid. That makes it a weak electrolyte. This is one of the 6 strong bases, and you know all potassiums are soluble. That's a strong base, and that is a strong electrolyte. Water's a liquid. This is a non-electrolyte. All potassiums are soluble. Strong electrolyte. If it is soluble, strong electrolyte. So this is where you would have H2SO3. It is aqueous. Because all acids are aqueous, it stays together because it is a weak acid. The only ones that will ionize are the strong acids and strong electrolytes. 2K plus and 2OH minus to break up your KOH. Solids, liquids, gases always stay together. 2H2O liquid. 2K plus and SO3 minus 2. So the only thing that is going to cancel is the K plus, and so that is your spectator ion. Your net ionic is H2SO3 aqueous plus 2OH minus yields 2H2O liquid and SO3 minus 2. And note, you should write somewhere that all ions are aqueous. All right, so anytime you put a plus or a minus charge, it's aqueous, or you can write aqueous every time. I prefer to just say every time I write an ion, it's aqueous. I'm not going to write AQ that many times. All right, so there are going to be easy questions on the test like this one, and harder questions on the test where they're part of something else. But remember that if you're asked for strong and weak electrolytes, if you can't do molecular ionic, net ionic, answer as many things as you can to get as much partial credit as you can. All right, so this is soluble, so that's a strong electrolyte. That's a hydroxide. That's a strong base. H2S. All right, that is a weak electrolyte. All right, and they're telling you that we're talking about acids. That's a weak acid. That is not one of the 6 strong. This is a weak electrolyte, and this is a strong acid and strong electrolyte. So make sure you have your solubility rules memorized. All right, we will be reviewing for the next 2 days for the test on Thursday.